Go like this because it's kind of hard to see. So.
Where'd he go?
Trying to get in the basket.
Yay, you're so little.
Okay, ready?
Ready.
Okay. So, we have talked about acids and bases so far, and I said yesterday that not all acids are bad for you. Okay? But yet other acids are really dangerous and explosive. You can do a lot of damage. Okay? For example, if you got perchloric acid on your clothes, it would disintegrate your clothes and then your skin afterward.
Oh. Got him.
However, if you were to get a little bit of lactic acid on you, it wouldn't do a thing. Well, if it was in your muscles.
Yeah.
Okay? So the question is, what is the difference between one acid that can severely hurt you and harm you, and another acid that doesn't really do anything to you? Okay? The main difference is in the acid's ability to get rid of its hydrogen ions. Acids that can give up their hydrogen ions easily and readily are nasty ones. Acids that do not give off their hydrogen ions very easily or readily are not so bad. Okay? And the same can be said about a base as well. Okay? So, has anybody ever heard alkaline before?
Yeah, like the
Like the battery.
I would say,
Alkaline.
yeah, we had an alkaline earth metal. Alkaline is another word that they use for something that is basic. Okay?
Girl.
So an acid you would say is acidic. Something that's basic you could say is alkaline.
you're so alkaline.
Okay?
Tomatoes alkaline.
Alright, so we are going to talk about a little bit of equilibrium stuff today, but before we do that, we need to talk about how water does some really unique things. Water, believe it or not, reacts with itself.
What? Since when?
Okay?
Does it mean astronaut?
It's called self-ionization of water. Okay? Yesterday, I don't know if you guys remember, I stated that water can act as either an acid or a base. Okay? And there's a name for things that can act as an acid or a base. They're called amphoteric substances.
Wait,
Oh.
when you have H2O that's an acid and H2O that's a base, that makes salt. Is that why the ocean's so salty?
No.
Okay.
Not that I don't think so.
Okay, don't laugh at me. That's a totally engaged question.
So technically,
Yes.
water reacting with water does not produce the salt. Okay? It's a little tricky. If you have an amphoteric stuff, water is completely separate from all the other things in its uniqueness. Okay? When I say water reacts with water, it doesn't mean that a ton of it will react. Like if I have a beaker of water, there's a very, very, very small amount of that water that will react with itself. Because the equilibrium of water reacting with water lies far to the left. What does that mean?
React to the side.
Yeah, so if I have a beaker of water, most of it's just going to be water. A very small amount of it will react to produce these guys. Okay? Now, on the next slide, I'm going to show you that this and another thing I'm going to use interchangeably. Okay? And you're probably wondering, why am I showing you that water can react with water? Well, the equilibrium expression that we get from this is where we derive our pH scale from. Okay? Which we'll talk about as we progress a little bit here. But before we do, I want to get just some vocabulary here. I'm going to be using these two things interchangeably. Okay? Because usually, for example, if I put hydrochloric acid in water, it's probably not the best color to use, huh?
You I got you, Hammer.
Got one. So say I have hydrochloric acid.
I feel like his pockets are like the very opposite.
Okay? This is my acid. What will it do?
It'll
Give off its what?
hydrogen.
Okay, and who is it going to give it to?
The water.
Which will produce?
H3O.
plus.
Okay? Plus
Cl minus.
Cl minus. And we can say, this is my acid, this is my base. Okay? This is my conjugate acid-base pair. Okay, so this would be the conjugate base of the acid. Okay, this is a base, this is going to be the conjugate acid of that base. Okay, like we talked about yesterday. Now listen, we said, I don't know if you remember me stating this, but acids and bases are usually done in what?
Water.
Water. Okay, they're usually done in water. So a lot of times, since all acids and bases are usually just done in water, I usually don't even write the water. I'll usually just go like this. HCl breaks up into H plus and Cl minus. So because of that, because we assume that all acids and bases are usually done in water, I use these two interchangeably. Does that make sense? Because if this were in water, that would be bonded to what? Water producing that. So I'm going to use those two things interchangeably. So whenever I say H plus, I'm also referring to H3O plus when I'm reacting with water. Okay? Just something that we have to get an understanding of. And we know what hydroxide is already, so I'm not going to say anything more about that. Let's progress here. This is a pretty easy question. What would you guys all say?
Protons.
Thank you, Brevin.
Oh, okay.
Acids?
Whatever. Brain's not there yet.
Yeah, they're fully there. All right, Gage, answer this one.
What is formed by the protons released by acids? Hydrogen.
Good job.
No, that's the thing we just talked about. H3O.
Okay, hydronium is H3O plus. All right, now I want to show you this. Okay. Self-ionization of water is this reaction. Water reacts with itself. Now, does it do a lot of it? No. Okay, it does not react with itself a lot. Okay, so really I will have mostly water and very little of this, but there will be some of it. Okay, could we write the equilibrium expression for this particular reaction? Okay, we could. Okay, KEQ, this products over reactants, but remember this is a what?
Liquid.
Liquid, so that's going to cancel out or just be 1. So, the equilibrium expression for the self-ionization of water is this. The concentration of your hydronium times the concentration of your hydroxide. Okay? Now, if this goes up, what happens to this? It goes down because this is a what?
Constant.
It's a constant. So if one goes up, the other has to go down. Okay? So if I put an acid in water, this is going to go up, and this is going to go down. If I put a base in water, this is going to go up, and this is going to go down. Okay? Accordingly, it will always give me the same constant. Okay? But one can go up and the other can go down. Now, you're probably wondering, great, we've got this equilibrium expression. Well, we derive our pH scale from the fact of how much hydronium do I have in solution. Okay? And if I have an acid in water, I have a lot of hydronium in solution, and it's really acidic. If I put a base in water, I have very little hydronium in solution, and it's basic, which I will show you when we start talking a little bit more about the pH scale. Now, instead of writing KEQ or KSP, it has its own name. Not its own name, but its own symbol, KW. What do you think the W represents?
Water.
Okay, we're going to see a KA later. What do you think the A represents? Acid. And you're going to see a KB later. What do you think the B represents?
Base.
Okay, but they're all equilibrium constants from which we can write equilibrium expressions of. Okay, there is what the constant always is. Now I say always, but the reason why I'm going to say always is because we're going to kind of deal with it at 25 degrees most of the time. if I have, sorry, if I have a water solution, okay, whether I put acids or bases in it, the Kw, or the equilibrium constant for that, will always at 25 degrees be that. Okay? So if I put an acid in that, like I said earlier, I will have, that concentration will go up, and this concentration will go down, but those two numbers multiplied by each other will always give me what?
1.0.
Yep. 1 times 10 to the negative 14. That's an important number. Did I give you that equation in your notes? You need it. You will use it. Okay. So, if my H3O plus concentration were 1 times 10 to the negative 10, I know you can probably see it up there, but what would be your hydroxide concentration be? Is that an earth-shattering mathematical phenomenon right there? No. Okay? Now, are you going to deal with 1 times every time? No. So you're not going to be able to just simply add the exponents all the time. It's just a quick way to show this so that I don't have to go through a ton of calculation. Okay? If the H3O is high, then the OH minus, oh, that's a problem.
Don't worry.
Yeah.
No, yeah.
No. Oh boy.
Is this our last chapter?
Probably.
Yeah. Oh, yeah.
I only say dang it because I need to raise my grade.
I don't even know what happened.
But at the same time, I don't want to lower my grade.
Alright, here we go. Okay. So, let's do this. Okay, we've got a situation where I've dissolved something in water, and I found that my hydronium ion concentration is what?
5 times.
Okay? And I want to figure out what the concentration of hydroxide is. I know it doesn't say that up there, does it? But that's what you're trying to find the concentration of. How do I go about doing this?
Subtract 1 to 1.
You will not subtract the exponents, so that's not one. Okay? So, I'm going to use the Kw equation. 1 times 10 to the negative 14 equals the concentration of H3O plus times the concentration of OH minus. And I know which of those two.
The H3O.
Okay? So what would I do to solve for my OH concentration? Divide. Everybody see that? You're going to take this, you're going to plug it into the equilibrium expression, similar to what we did last chapter. You're going to divide it to solve for your concentration of OH minus of this particular situation. Okay? Do it. Is it not in your notes?
Oh, yeah.
Wow. Oh, shoot.
Anybody got an answer?
No.
If our calculations are correct, 2 times 10 to the negative 8.
Do I have an amen to that? If his calculations are correct, you guys don't have your calculators up?
2 times 10 to the negative 8.
Okay. I need what with that though?
Molarity.
Molarity. Alright, there's your answer. Hard math, huh? Now you're going to find that this chapter has a good amount of math, but it's not overly difficult math. Which is kind of. Okay? Everybody get that now?
No.
You didn't get that?
Like what it is.
Oh, it's times 10 to the negative 14. Not 4. That makes sense?
Yes.
Tanner, how about now?
Oh, hold on. No, you can keep going. I know that.
Oh no.
Okay.
Logarithm?
Alright, oh, that's why. I just didn't finish.
Yeah, you got it.
There it is. Alright, pH scale, here we go. Yes, we are going to use logarithms. I cannot say it very well.
Logarithm?
Take it.
Logarithm.
Words are hard, okay? No. Okay, so pH.
Logarithms?
Log the limbs.
Okay.
Okay.
Logs.
pH stands for power of hydronium. Okay? When I say the pH is something, what that is telling me how much hydronium I have in solution. Okay? So if it's really acidic, I have a lot of hydronium. If it's basic, I don't have very much at all. Okay? Now, here are, this is kind of some silly examples, because do you think that you're going to be given concentration 1 times all the time? No. So, if I go back quickly, this is your equation to figure out the pH. You find your H plus concentration or your hydronium concentration, using them interchangeably here. I just take the negative log of that. Do we know where the log is on our calculator?
Yeah.
Okay? If you have a hydronium concentration of 0.05, you would do negative log of 0.05 and you would solve to find the pH of that.
1.3.
Okay? So, we've got 2 equations now. We got 4 more to go.
Oh my word.
Nice. Okay, so quickly, this is just a short method. Don't assume that you can just look at the exponent and assume that's the pH, because that's only when you have 1 times. Okay? So I even hesitate to even show this to you, because then everyone seems to think you can just use it all the time. Here is the scale for if something is acidic, basic, or neutral. Right? If the pH is 7, I will say that it is neutral. Now, what neutral means is I have equal amounts of hydronium and hydroxide. Let me show you. This was my KW equation, right?
Yeah.
I'm just going to modify and not put H3O. Okay? If I'm neutral, these need to be the same. Negative log of that gives you what?
7.
So a neutral solution is a solution in which you have the same amount of hydroxide and hydronium or pure water. That doesn't happen very often, obviously. Okay? If the acid goes up, when you take the negative log of that, you will get a pH of less than 7. And you can actually have a negative pH. That's really acidic. Not good stuff. Okay? Basic things are anything above 7. And you can actually have higher than 14. That's really bad. That's really basic. Okay? That will do some damage. Alright? Your water will be, your okay drinking water that will not hurt you is in between a pH of 5 and 9. Okay? If your drinking water is either below 5 or above 9, you probably shouldn't drink it. Flint, Michigan.
Wait, so the more acidic has more hydrogen, and
Yep.
the more basic has more.
Hydroxide. Yep. Alright. Let's do this problem. Not an overly difficult problem. Okay? It says the hydronium ion concentration of shampoo is this. Okay? How do I find the pH if I know the hydronium concentration? Is it
The negative log.
Negative log.
negative log
Log.
of 2.0 times 10 to the negative 5? Plug it in, tell me what your pH is.
4.7.
Okay, so if we have a 4.7 pH, is it acidic, basic, or neutral?
That's definitely
It's
acidic.
acidic. Okay? So I would just put that it's acidic.
Not safe drinking.
So, do I have more hydronium or more hydroxide in this case?
Hydronium.
More hydronium. You're acidic if you have more hydronium. You're basic if you have more hydroxide. Okay? Now, I want to make something clear here. They may not always give you the concentration of your hydronium. They may say something like this. The concentration of HCl is 0.01 molar. And they won't tell you anything else. Last chapter, we talked a lot about ions dissolving, correct? Okay? Well, won't this break up into its H plus and Cl minus? So if I know the concentration of this, I know the concentration of that. They're the same. Could I do this with a basic thing as well? NaOH. Okay, if this is 0.05, then I know the concentration of that, since everything is a 1-to-1 ratio. You're not going to see any acid or base that's not a 1-to-1 ratio, thankfully. It's not impossible. Okay? Because they get rid of their ions one at a time. And we'll talk about that later. Alright. I'm going to skip this one for the sake of time. It is a little bit more difficult. Let me kind of walk you through what you would need to do though. Wait, yeah, okay? They gave us mass. Don't we want concentration of hydronium, right? Okay? Concentration is molarity, correct? Which is moles over liter. So what do you think I need to do to this?
Convert.
Convert to? Moles. How would I do that?
You would go.
Molar mass, right? Periodic table?
No.
Stop it!
I don't even
Stop
know
it!
anymore.
Stop it! I'm going to do this because you guys are buns right now.
You just call us anuses.
Buns are not anuses.
Do you?
Is your bun your anus?
That's what saffron.
You know what an anus is?
No, that's a cool saffron.
Okay.
Okay.
Alright, for every 1 mole, I've got to find the molar mass of high.
E-teacher.
Okay, there's not many of you who are paying attention.
So 1.01 plus.
Plus 120 something.
I can't see.
126.9.
9.
So 126. 126? Wow.
127.
127.91.
Divide it.
Okay? You figured out your mole number?
Wait, what just happened?
Converting.
You were thinking about anuses too much.
No, I'm confused what you just did. I'm paying attention.
Alright. I'm
This is what
adding mass to moles using molar mass. Because I want,
Three.
Why did
in
you
order to
add,
find the pH, I've got to know the molarity of my hydronium.
why'd you add stuff to the grams?
What are you talking?
Alright, can we simplify this?
That's grams, he's going grams to moles.
Okay, how so?
Yeah, why did he add something to that 126?
I don't know, okay.
Because it's 2.
Because I have hydrogen and iodine.
It's like, it's like this.
Okay, got
Like
it.
grams to moles, it's like, okay.
I thought it was
need
just hydrogen.
5
Can I get a
slices
number
of
for
pizza.
me? Thought.
You need
Uh,
five.
0.03127198.
0.003.
What?
3 what?
127.
Oh.
127, so that is the moles. Then you divide that by the,
Liter.
and I have it in milliliters.
So you just go.
So let's just convert this to liters quick. Whoop, there it is.
There it is.
And divide to get the molarity. What do we get?
This one.
0.006. Now, that is the concentration of high. But what did I just say a second ago? If I know the concentration of this, I know the concentration of that.
Okay.
It's a 1-to-1. So that is the concentration of my hydronium. Okay? So, to find the pH, you would do what?
Plug it into the lobe.
That's gonna be really one way.
2.22.
Just kidding.
2.2 what?
Doesn't make sense.
6.7.
Well, it's really acidic.
2.
Not really.
Okay?
Really acidic would be
Where'd
like.
you get the 0.5 liters?
If it's 0 to 7 and it's 2,
500 milliliters.
and it's
of
pretty
liquid.
acidic.
Right?
It can be, but it's really acidic as it is.
Wait.
You want what?
There we go.
Oh, because moles per liter is molarity.
What about us? Alright. to finish this lesson tomorrow.
Wait, but today's Friday.
I'll finish Saturday.
I'm working.
What I would do is I would do what you can in your homework. What?
Let's see. The market starts tomorrow.